Okay, thanks everybody for your attention there. Just a brief diversion. We're going to be celebrities and be recorded here, so new experience for me, so bear with me. As I said, for those of you who just arrived, I'm Kevin Kelly. I'm the director of one of the engineering programs here, but I'm going to talk about the Department of Mechanical and Manufacturing Engineering, which is where I'm based. So, what's mechanical and manufacturing engineering? What is it for me? That's more or less what I'm going to talk about, and also what will it mean for you. So the first thing I'd just ask you to do is just think of 2 or 3 words that come into your mind when you think of engineering. Okay, anybody like to volunteer a word?
Innovation.
Very nice, I like that. Yeah, anybody else? Nobody else, all very shy. Okay, who taught bridges? Nobody, that's brilliant. Okay, normally everybody thinks bridges and I hate that, so that's great. Okay, innovation is actually an interesting word. It's one nobody's ever said to me in any variant of these talks before, but it's one which is very appropriate, as we'll see. So what kind of skills are required to be an engineer? Because after all, if you're at this talk, presumably you're at least interested enough in engineering to want to know a little bit more about it, and ultimately you're asking yourself the question is, should I be an engineer? And to give you some kind of idea of whether or not the answer to that question is yes, it's useful, I think, to look at what are the skills that a good engineer requires. And I've put them down on the slide here. So creativity. Maybe this isn't something that we think about instinctively with engineering, but my friend over here says innovation. That's exactly what it is. It's creativity. It's coming up with new ideas and concepts. So synthesis, we have to be able to bring complex information together. So as an engineer, one day I might be working with a nuclear physicist, the next day I might be working with the doctor, the next day I might be working with the train driver. So it could be very different people and very different skill sets, and I've got to be able to bring information from all of those domains together. Problem solving, that's the heart of engineering. If you wanted me to sum up what an engineer does in 2 words, I'd say solve problems. That's what we do. Why do we solve problems? Because they're there. There's challenges out there in the world, and it's up to engineers to meet those challenges. And one of the other skills needed in doing that is analysis. So synthesis and analysis are the 2 sides. Synthesis being bringing the information together, and analysis being able to look at complex information and distill it down to its core. And a very important skill for engineers these days, and one that is often neglected in terms of what people's perceptions of engineering, is the ability to deal with people from a wide range of backgrounds. And that's not just technical backgrounds, but also cultural backgrounds. So increasingly, engineering is a global profession, and you might have project teams which are based all over the world. So I might be liaising with somebody in India, somebody in South Africa, somebody in Japan, somebody in Germany. We all have different cultures, different languages, different ways of doing things. So you've got to be able to get on with that. So ultimately, I want to finish this slide on a positive note. You can do it. So if you see any of those skills in yourself, and obviously bear in mind these are things you learn and develop as you go, but fundamentally you'll have an idea. Do you like analysing things? Are you good at bringing information together? Do you like solving problems? Do you like challenges? If there are things you see in yourself, then you can be an engineer. So don't let anybody tell you different. And particularly for any girls in the audience, and I'm delighted to see there are lots there, don't feel it's a profession for men. There are men in it, there are women in it, and there's no reason why we can't have more women in the profession. So if you have the skill set, you can be an engineer. So what do we mean by engineering? So I thought I'd throw up a definition here. And this is one I quite like. It's a little bit wordy, but let's just look through it. So it's the use of human intellect and creativity to responsibly harness our environment for the betterment of humankind. You could have read that. However, let's break it down. Human intellect, so that's smarts. Creativity, so that's our creative side, obviously, the other half of our brain. And what we're using the creativity and the intellect for is to responsibly harness the environment. That is, we have to take what's around us and we have to use it in a responsible manner, because we've got to think about making the world a better place, and we've also got to think about the future of the planet and the future generations beyond us. So we have a responsibility to be responsible in terms of our use of resources and to direct that effort towards something that's actually fundamentally useful and makes the world a better place. So some examples. So at the end of the 20th century, so 1999, the National Academy of Sciences in the US met, and one of their tasks was to come up with the 20 greatest achievements of the 20th century. And they come up with a list of 20 great achievements. And one of the interesting things for me about this was what it does really is it sums up, if you like, what's the difference between the 20th century and the 19th. Because all of these are things that were developed by mankind during the 20th century that weren't there beforehand. So here they are. The car, the airplane, electronics, radio and TV, mechanized agriculture, computers, air conditioning, refrigeration. So we look at, there's more, space exploration, household appliances, washing machines, dishwashers, etc. Health technology like antibiotics, artificial implants, petrol and gas, nuclear power, new materials. All of those things are huge advantages. Now that mightn't seem that impressive, but actually stop and think for a second. What would life be like if we didn't have any cars? What would life be like if you had no fridge? What would life be like if you stepped on a nail and there was a significant chance you'd die if you got an infection because there was no antibiotics? What would life be like if we didn't have access to clean drinking water? What would life be like if we had to grow our own food, everything we ate? Some people like to do that, but if we all had to do that, the world would be a very different place. So all of those differences are things that made the 20th century different to the 19th. And in 80 years' time or 90 years' time, somebody would be able to draw up an equivalent one for what made the 21st century different from the 19th. And what all of those things have in common is they're all engineered technologies. So without engineers, none of those developments would have happened. So in other words, engineers are the people who drive the present from the here and now into the future. The people who make the future happen and make the future real. So this generation, you people here, you're going to be the engineers of the future if you decide that's what you want to do. And then your responsibility will be to create the different environment and the different world for the 21st century. So somebody in 90 years' time will be talking about the things that your generation have come up with that made the world a different and a better place. So what kind of challenges are out there for the 21st century? Anybody like to suggest any? What kind of global challenges are there?
Global warming.
Global warming. Food prices, yeah. Anything else?
Gas running out. And petrol.
Yeah. So natural resource depletion. So there's lots of challenges out there. I just threw a few up here. One that's topical at the moment, the banking and financial crisis. Energy and the environment. So global warming and where we source our energy from. Poverty. So who's going to fix all of those? And the answer I'm going to propose to you is engineers. Okay, we're not going to do it on our own, and obviously I'm biased, but as we'll see, there is actually a lot of sense behind saying engineers will provide the solutions to all of those. And that might be a bit surprising. You might say, well, what have engineers got to do with the banking system or the financial crisis? Or what do engineers have to do with energy and the environment? Maybe a bit more obvious. What do engineers have to do with poverty or global health? Not so obvious, but let's have a look. So talking about the banking crisis, for example, one of the major lessons, hopefully, that we've learned in the last few years is, as an economy, we can't simply depend on services and sales to sustain the economy. Ultimately, economics boils down to something very simple. If you want a country to get rich, there's only two ways you do it. You make something, or you do something cheaper and more efficiently than anybody else does it, or you dig something out of the ground that somebody wants. They're the only two ways you get richer in the long term. Everything else after that's a bit of a distraction. So we can't just depend on buying and selling houses to one another, or cutting each other's hair, or making each other cups of coffee to make ourselves rich. We need something a bit more fundamental. And the way we're going to do that is by providing high-value products, because Ireland is a country where we like to pay ourselves reasonably well in comparison to certain parts of the world where they make things. So we can't be making things like clothing, for example, in this country. We can't be making low-technology parts in this country simply because it's too expensive. We can't afford to pay the wages that people in this country need to live. So what we need to do is we need to be producing high-value products, computers, medical devices, automotive components, things that take a lot of technology and a lot of skill to build. And we need to be able to innovate so we can compete and continue to stay ahead of all the other countries that are trying to do the same thing. So when we talk about making things like that, nothing gets produced without engineers. And mechanical and manufacturing engineers are all about things that move and all about making things. So a good engineer needs an ability to think across a full spectrum. You need to be able to move from the technical to the business and back again. So you need to be able to make a technical case for a new idea or a product, but you also need to be able to justify that financially. You need to be able to estimate costs. You need to be able to think of the impact on the world around you, etc. And one of the things about that skill set is that when you graduate as an engineer and you have that ability to think across a wide range of disciplines, and you have those skills I talked about, the analysis and the synthesis, that means you're able to take a lot of information, very complex information from lots of sources, and you're able to distill it down and make conclusions and make decisions. Think about that skill set and where that's required. That's required at top-level management everywhere. So it's no coincidence that 40% of the chief executives of the top 100 companies in the world are engineers. Right? Much higher than the percentage of engineers in the workforce, and the reason is because it's the way they think. Specifically, returning to the Irish context, we're interested in manufacturing and mechanical engineering. There's a big shortage in Ireland. So a lot of you are probably worried. You say, well, maybe engineering sounds interesting. It appeals to me because I like maths, or I like problems, or I like whatever. But will I get a job? Yes, there are some areas in engineering where there's some shortages of jobs at the moment, and there are areas where there's a glut of jobs at the moment. So in the manufacturing sector, for example, there's a shortage of jobs, and that shortage is projected to last until at least 2020. So we have to continue importing engineers to meet the needs of Irish industry, and not just multinationals in Ireland, domestic Irish industry doing the things I talked about, producing high-value products. So in Ireland, you may or may not know, we have a big concentration of pharmaceutical industries. We have also the second largest concentration of biomedical industries and also of electronic manufacturing. So we have a lot of high-tech manufacturing in this country that's kind of hidden. Okay, let's bring it back to, that's the, if you like, the role engineers have to play in the financial crisis. More engineers means we fill these jobs ourselves, we generate more wealth in this country. The next thing I had on that list of challenges of the 21st century were things like energy and the environment. So let's look at energy. 85% of the energy content of our sources of energy, so that's whether we take coal or oil out of the ground or natural gas or wherever we get our energy from, 85% of that is lost in the transition from the raw material into the products and services we use. Which means, as a consumer, all of you, you may have heard of the campaign called the Power of One. Anybody heard of that? A few of you probably heard of the Power of One. So this is kind of a campaign to get people to do things like don't leave your TV on standby, switch off the lights when you go out of the room. That's the reason. Because 85% of the energy is lost, if you choose not to use 1 unit of electricity, you save 6 units of raw material. So there's this huge multiplier effect that we get as consumers by being more efficient. As engineers then, we're on the other side of the equation because we're the people who transform the raw material into the energy. That's one of the things mechanical engineers do. So if we can reduce those losses, so if we can get from 85% losses to 75% losses, we could reduce the consumption across the world by about 50% or over 50%. So we make a huge difference in terms of the energy consumption and the usage of natural resources. And in practical terms, that's when are we going to run out of oil? When is it going to cost me €5 per litre to fill up my tank with petrol? So these kind of questions are there, and the solution to those is partly in managing the demand, that's us as consumers, but also engineers have a huge role to play in the efficiency side. What kind of things do I do, or do my colleagues that I work with here in Trinity do? Well, here's an example, and this addresses the third point of poverty. So there are 2 billion people around the world who use off-grid fuel-based lighting. That is 2 billion people. Think about that for a second. 400 times the population of Ireland. 450 times the population of Ireland. Those people do not have a switch on the wall that turns on the light. They don't have a socket on the wall to plug something into. They do not have electricity. The only electricity they have comes from batteries. So for lighting, they have to burn fuel. And on the top there is a woman in Mali, and you can see the light she's getting is coming from a kerosene lamp. On the bottom, you have students in Lagos, and they're studying on the street because that lighting is free and they don't have lighting in their homes. To generate that lighting, 2 million barrels of oil per day are consumed, and that's a pretty high cost. So 10 to 30% of salary costs in the developing world have been spent on lighting. That compares to a fraction of that, maybe 0.1 to 0.5% in the first world. So a huge difference. 20% of the money spent in the world on lighting is spent in this manner. But only 0.1% of the energy, lighting energy, comes out. So it's a very poor investment in terms of generating light. It's not renewable, so it has consequences for the environment. There's a big health hazard associated with it in terms of cancer risk and fire risk. And the solution is something one of my colleagues has been working on called the eternal candle. And what we do here is we try and trap light during the day and release it during the night. Now, how can you do that? You can't just open up a box, fill it with sunlight, close the box and open it at night. It doesn't work like that. It's not like filling a container with water. So what we've got to do is we've got to transform the light energy into a different form of energy. And that's what we do here. We take the light energy here during the day and we use it to heat up some wax, and the wax melts during the day. As the temperature goes up, I'll have to work my way through this animation. Oops, there we go. And then at night time, we have a container of liquid wax which as it cools down turns back into a solid. And when that happens, there's heat released. That heat is called the latent heat. So you might remember that from your science course. Latent heat of vaporization, latent heat of vaporization in this case, or sorry, liquefaction in this case. We're going from a solid to a liquid. So we can capture that energy as it's released, the latent heat, and we use a device to turn that into electricity. Here's an example of the output. On the left is a page of a document using a paraffin light, and on the right is the same document using the eternal candle. Significant difference, and effectively now this is free energy, no cost, no oil, no pollution, no cancer risk. Simple, low cost, makes a big difference to the world. I might skip this example, we're running short on time. Here's another example of something that I'm involved in, which is the area of micro manufacturing. So increasingly we have requirements to make things smaller and smaller for a whole range of applications. It can be making very tiny devices to go inside the human body. It can be making smaller and smaller components for your mobile phone. Wide range of applications. So how do we make something really, really small? What happens? How do we go about making something maybe that's too small to see? That's a bit of a challenge. So again, we've got to get creative. Why did I put up some statue there with no arms and naked torso? Well, I like it, but we get creative and we actually make objects. It's the Venus de Milo, by the way, that's cultural. So we can do something called three-dimensional printing. We can print objects. And any of you have been over at the display in the printing house, you might have seen the human skulls on the table. Well, they're not human skulls, they're models of human skulls. They're made with this method. We print these objects using lasers and special plastics, and we can make them big or we can make them small. Now there's 3 Venus de Milos. Anybody know what they're resting on?
Human hair?
Yep, human hair. Okay, so pull a hair from your head, think of how thick that is, and you get an idea of the scale of those. So they're manufactured. Now it's not all about making pretty little statues to stick on your hair, because nobody would see them. Sometimes we have to make things which have maybe a more, serious purpose. So, an example of one of those is this micro scaffold, and this is used for generating of human tissue. So we can take a tissue sample from a person, we can grow that tissue sample in a lab, so maybe the person has had a degenerative disease, or cancer, or been involved in an accident. We can grow that tissue, and this scaffold acts as a structure for the tissue to grow around, so it grows strong and healthy, and then we can put that tissue back in the body. So we just stick a needle into you, pull out a small little needle, like any injection, pull out a tiny amount of material from you, just DNA essentially, put that into a test tube, we grow the material around the scaffold, and then we can replace cartilage, muscle, bone, or whatever. There's another example. People who hate needles might like this one. These are microneedle arrays. So basically these can be used for injecting people, and the needles are so small that they actually fit through the pores in your skin. So they don't actually pierce any nerve endings and you feel nothing. So you just basically press one of these on your skin and you can absorb the drug or whatever you need to inject very easily and very painlessly. Another device, a stent. Anybody who's had any relatives who maybe had some heart trouble, you might know what a stent is. Anybody had any relatives with a stent fitted? Yeah. So an angioplasty, maybe you might be more familiar with the term for those who've had it fitted. And very briefly, what happens when somebody has heart disease, what happens is you've basically got a blocked pipe in your body. You've got these pipes that pump the blood around your body, and they get blocked over time with this substance called plaque. And those blocked arteries can lead to a lot of problems. Heart disease, stroke, gallbladder, etc. The traditional way of dealing with that was to bypass it. It was kind of saying, okay, we've got a blocked pipe, let's just put in a new pipe and route everything around it. So what they did before was they cut you open, literally Black and Decker down the middle of your chest, pull it apart, stick in some new piping. Pretty dramatic operation and pretty traumatic for the patient. The modern treatment is far less invasive. My father had one of these fitted last Monday. Took 1 hour. He wasn't even under anaesthetic. So we can now treat disease like this really, really quickly. And here's how we do it. So this is a model here of a human artery, and you can see this material in the middle there, that's the plaque. And what we do is we insert a very small device either through your artery in your arm or through your leg. And this device is a really thin little tube with a balloon around it, and this gets passed up inside the artery, and around the balloon, as we'll see, is this small little wire mesh called a stent. And as we pass it up towards the blockage, the doctor can see this using a special camera. We can see where the stent is, and once we get that into the correct position, we inflate the balloon, it pushes out the stent, and reopens the arteries. The artery is blocked, which stops the blood getting through. And we put the stent in place. It forces the artery open and allows the blood to flow again. We then deflate the balloon and take out this wire, which is called a catheter, and we leave you with the stent behind. So we'll just show you that on an animation, hopefully. Okay, doesn't want to show you. Right, that's Apple Macintoshes for you. Okay, some other things I might be able to show you in a second when we have some questions. Some other things here, some new materials. So a whole area of engineering is not just thinking about new ways to do things with existing materials, it's about developing new materials. So you don't dig steel out of the ground, you make steel. You don't dig plastic out of the ground, you make plastic. And all the time we're developing new materials. So anybody play tennis or ski or play golf? Even modern bicycles, carbon fiber. There's an example of a modern material. So we're constantly working at developing new materials, and some of my colleagues have worked with these. So here's an example, shape memory alloys. So here's a pair of glasses, and anybody who wears glasses might have had problems occasionally. You put your glasses down, and then you stand on them, or you sit on them, or you let them fall, and your glasses are bent out of shape. Shape memory alloys, you could fold up your glasses, stick them in your pocket, take them out, and they pop back into the original shape. Biodegradable plastics come in. I'll skip this problem here as we're running short on time. Okay, there's some things about mechanical and manufacturing engineering, why you might want to investigate those. Why would you want to come to Trinity to do those? Well, a lot of reasons. We're a campus university. We're in the centre of the city, so we're easy to get to. Lots of things happening around the place. We have a broad curriculum, meaning you can study a wide range of subjects. We have the tutor system, meaning every student gets a member of staff to look after them and help them through the college. We have scholarships, biggest library in Ireland, and lots of sports clubs and societies. If you are interested in doing engineering, we have two options. There's a general engineering degree, which is 2 common years, after which you specialise in one of 4 disciplines. That was 405 points this year, and the class size is 165. And the other engineering degree is the Engineering with Management degree, which is my baby. And for that, you're based in the Mechanical and Manufacturing Engineering department. The main differences being you have a significantly larger business and management component, and we have a smaller class size of only 20 people. That was 380 points this year. What happens after graduation? There's just some diagrams. I won't dwell on them too much, but you see some of the people who employ our mechanical and manufacturing engineers. You also see about 1/3 of our graduates go on to do further study. They like the university system so much. Money, for those of you who like money, about 30,000 euros is the current starting salary for graduates. So I'll just conclude by saying our future is in your hands. You're going to be the engineers of tomorrow, hopefully, and these are some of the things that are going to be the challenges that are in front of you. So I'll leave it at that, and if there are any questions, I'll be happy to take them, and we're going to have a panel discussion now in a couple of minutes for all of the engineering streams. Anybody like to ask any questions? Yeah?
I see that it says like you go abroad
Yep.
you go to like a non-foreign country if you're not doing language.
In principle, I think you probably could, but I wouldn't see much point, to be honest. The whole point of the idea is to actually broaden your language skills and your cultural experience. Yep. Yeah, the question was, is it very practical? Yes, there's a lot of practical work in it, but it's not just working with your hands. There's a lot of analytical and theoretical work there as well. But you are trained.